Hello everybody. What I'm going to attempt to do is use two cameras, a light board, and a document camera to be able to explain to you a very quick, big picture of how the network works. Now, you've had all these terms already, and what I want to bring out is some of the finer points and how it all fits together. Okay, so what you're looking at is the OSI layer mnemonics here. So here's our layers, and then on the way down you can remember it as that all people seem to need data processing. And where do you need to know this? You need to know it for the Network Plus and for job interviews. In the real world, you use the OSI layer as an abstraction model to help you troubleshoot. Okay, is it a layer 1, layer 2, layer 3? That's where it comes in industry. And then on the way up, I use the term programmers do not throw sausage pizza away. And this is all just to kind of help you remember how the stack works. Okay. Now, what happens when you send a message over the internet is that it starts up here. You say, I'm going to send an email to a friend. You say, hi. And the email starts here, and it works its way down and then gets encoded into signals, like waveforms like this, that represent ones and zeros, and it gets put back together, coming back up, and and the person you send it to says hi on their screen, and it comes over email or whatever. Now what happens is that when you send your message hi, the first thing it does is that the application header puts on some data, and then the presentation header adds some data, and then more header information is added, and then more information is added, and then more information is added. You get the point that one little tiny message, hi, which in our case here is going to be 8 bits, 16 bits, pretty tiny, but a single packet that gets sent over the web is 1024 bits. So even though this is 8 bits, what happens is all this information gets encoded into your message. Each and every thing that gets sent over the internet gets this header added to it. Everything. All your mouse clicks, anything you do on the web, anything anywhere gets encapsulated so it can go over the web. Okay? And then what happens is we have our class A, B, and C addresses here. And we have the one you're probably familiar with is 192.168.1.1. Well, that's a class B address. And this is how many hosts you can put on one network. I will tell you, in the world of TCP/IP, if you get this many hosts on a particular subnet, it's going to be really slow because there's too much traffic. And then IP6 brings a whole new world to this. And then here's another example of your class A, B, and C. Now, so you can see there's more host information, less networks, and then all the way down here to class C, you have not too many hosts, but you have a lot of subnets. And then here's the masking. This is, you've probably seen this. This is your net mask that you probably run at home. And this is what we run at school because we subnet our traffic off fairly well. Now, I want to say all that to get you to here. And I got one other little place to show you. These are the port numbers of things that run on the internet. You can also, in the world of Linux, you can cat/etc services, and it shows you all the services that are available and what ports they're bound to. You need to know the most common ports for the Network Plus exam. Now, why is this important? Well, some of these ports should never, ever, ever be open to the internet. One of them is 139. This is Microsoft's ability. You know, when you go into Microsoft, you cruise a network neighborhood. Well, That's one of the ports is 139. That should never ever be open to the internet. So if it is, people can browse your network and do anything they want to your network. Okay. In the early days of networking in my neighborhood, I could see everybody's C drive. It was really kind of crazy. That was quickly remediated by a Microsoft patch. Okay. But here's what is in a packet. Okay. Now, I just want you to take a look, if I can get this to line up right, where you can see both of these. Let me go ahead and just do this. Fold it down. So what is happening is that this segment here, right here, is all of this data. Now, what I want you to notice is that up here, what do you have? There's an IP address. There's an IP address. There's a source port, 22, or a destination port. It could be 443 for secure shell. And there's checksums. And buried inside of here, there is also data on the MAC address of your card. So each individual network card has a MAC address. That MAC address is in every single packet that you send out to the internet. This is how the good guys and the bad guys find you. Okay? So basically, in a big picture, what we have is if you think of protocols as the air, everybody's in a room, and there's 30 people in a room. And you have 2 people speaking German, 2 people speaking Spanish, 2 people speaking English. They can all understand each other because they're using the same language. It's the same thing with the internet. You have all the internet flying around. You have all these protocols. You have DNS on port 53. You have SSH on 22. And you have web traffic on 80 and 443. So this is how it all works, is we get all these different protocols on the web, and they're always coming up with new ones. And they keep adding them to the internet, and the internet gets more and more expansive. So what happens is that when we go out and search for Google, and we type in www.google.com, we're using a service called DNS here. This stands for Domain Name Service. That converts a human-readable Google.com into an actual IP address. So if you go to your command line on your machine of choice and type in nslookup, and you type in either google.com or the IP address of google.com, it will return the name. Okay? So DNS is kind of a big deal. This is, if it wasn't for DNS, we humans wouldn't remember all the IP addresses that we had to surf to. Okay? And this dynamic host control protocol, this is what happens when you first turn your computer on, and your computer's really pretty brain dead. It doesn't know what to do. Once the operating system is running and it says, oh, I want to connect to the internet, it goes to the DHCP server, and the DHCP server gives it an IP address. And the DHCP server keeps track of the MAC address of your card. Okay? So the card and the IP are together, and they're held in something called ARP tables. So if you open a command line on your machine of choice and type in ARP, you will see the MAC addresses and the IP addresses that are allocated in the ARP table. Address Resolution Protocol. Now, there's a little blip in this. In the early days of the internet, we had our IP addresses like 198, and let's see, it's too far outside the window here. I can't. My window is a little small. Let's just go 10.10.10.10. Well, when the internet grew really, really fast, we were running out of IP4 addresses. We were running out of address space because everybody was connected to everybody else. And they said, what are we going to do? Or the internet's going to break. And this happened in the early 90s, late 80s. And NATD came up. Network Address Translation Daemon. What this does is it runs on your router. So you have a router at home, Linksys, 2Wire, whatever. and this NATD is running on your router, it keeps track of these 198.168.1.x addresses, okay, in your router. There's a RFC called RFC 1918 that says certain IP addresses you will never see in the wild. 198.168 is one of them. You will never see that in big network traffic, because all network devices, if they see something like that come over the internet, they drop it, because it's supposed to be behind your router and it never gets out beyond your router, okay? And so what happens is your internal address gets translated to some external address like 206.127.1.12, okay? All right, so your router keeps track of that. So when your information goes out on the internet, it gets all the packets smashed in there. This is the IP address that's put in there, and it comes back in, and then NATD looks up the IP address it comes in from, this one, and then translates it back to your 198, and it comes back to your computer. So all this magic is happening behind the scenes, and this is an extremely big picture of how this all works. And I included a very short little demo of Wireshark and how much traffic is actually captured from my 10-second screen. And all I wanted you to do in that video is just watch it so you can see what Wireshark is doing. So when you surf the web and you go to basic.5 HTML and it brings up hello world, and you can actually capture every single packet in that conversation between those two network cards. And this separates the people that really know what they're doing to people who think they know what they're doing. Is if you can understand what's going on at the Wireshark level, you will always remain employed, because it's very detailed. It's not hard. It hasn't changed hardly at all over 20 years, but people keep embedding secret little things in there, and they need better and better tools to break apart these packets to find the bad stuff in these packets. So this is how the Russians and the Chinese are getting into everything, is that they embed things, and then people don't really see it because it looks like regular web traffic. Well, it's not. It's actually something else. So you have to break open each packet, and sometimes it's packets inside of packets inside of packets, to find out what's in there. And this is why security gets paid so well. All right, and that is a super fast, quick overview of the big picture of how the internet works, with a lot of gaps in it. Anyway, all done. So we'll see how this stops here.